let's get started. Welcome to lecture 4 of the Algorithms and Data Structures course. Last class we talked about recursive functions or recursive code, recursive algorithms. And today the main thing we need to talk about is recursive data structures. So here we go. And this topic shows up on your lab in a big way, as some of you have already seen with the tree set implementation that you need to do. Where's my mouse? Okay, so just a quick note about why are we even bothering to do recursion. I think that may have been missing from last class. Like, it might have been fun, or it might not have been fun, but I didn't really talk about why we need to know this. So we saw some good features of it last class, like with binary search, the code maybe looking more natural being recursive. But I think today we're going to see a stronger motivation for recursion because we're going to do a bunch of stuff that would just be a huge pain to do any other way when we get to these trees. So what is a recursive data structure? I don't know if that's an official term, by the way. I just made it up. But maybe it is an official term. So we have talked about things like this, which is a list of lists. So this is a list with two lists in it. The first one containing 1, 2, 3. The second one containing A, B, C. We also had a dictionary of dictionaries in Lab 1 with the Markov model. And there's these Russian dolls that are like a doll within a doll within a doll, etc., etc. So we have seen that kind of thing, which I'm calling, I guess, nested. I have a dictionary within a dictionary. But what I want to talk about today is different from that. It's not some data type contained within some data type so much as when you define the data type in the first place, the definition of it is recursive. So what is a dictionary? Well, a dictionary is what we talked about, basically a hash table, and there's a bunch of ways you could define that. But when we talk about the data structures today, we're actually going to define them recursively. Okay, so the analogy I want to use for the first part of the class is this magical treasure box. And I have a bunch of code for the treasure box, which we're going to go through in the next few minutes. But let's first talk about what it does. So the treasure box is, well, it's a box of things. And it can hold two things inside of it. It can hold a value. So that could be a string. So in this case, I have a string. Initial box, and so there's enough space in there to put in this is the treasure, quote unquote, the value, the thing you're trying to store, but you can also fit another treasure box inside of here, we're assuming. So somehow that fits, even though the one inside can hold as much stuff as the one outside, somehow they fit within each other. And then what we're going to do is we're going to use this to basically implement a list-like data type. So imagine you wanted to make a list data type. So we made data types in the class like portfolio and stock and those types of things. But imagine you wanted to make a list and you were making a list, so you didn't have access to a list already. So we want to make it from scratch. So one thing you could do is you could have this treasure box inside, and then, I don't know, this would maybe have more stuff in here, and another treasure box inside there, and the list would basically end up being this was the first element, this was the second element, this was the third element, and so on. So the first element would be on the outside, and the last element would be on the inside. And this particular type of list that we're implementing, this treasure box, it has a couple of operations we can do to add things to it. So one thing I'll just scroll up for the code for a minute. So there's get, which we'll talk to later, but there's append inner and append outer. So basically there's two ways to add things to our list. We can put something on the outside, or we can put something on the inside. So the first code I have here, scrolling back down, is I'm appending something on the outside. So what that means is I actually started with this initial box, and then I added on the outside, and I can already see I'm going to run out of space, but that was bad planning. I added on the outside this string. So I basically added something to the beginning of the list, and then I did that again. And I guess I'll... Gosh. I don't know if everyone can see this, but you can imagine what it says. Wrap second box. Okay, so I've done those two operations, and I've run the code. And if I had defined a string function, I could have made the thing print out nicely. I don't think I did that. But this .get function is basically like the indexing into a list. It allows me to get the first thing, get the second thing, get the third thing. So if I get the 0th item, I get wrapped second box, because I added that to the beginning of the list. And if I get the first thing, item 1, we're indexing from 0 here, just like with lists. So item 1 would be the next one, and item 2 would be the next one. And then item 3, in this case, it's just returning none, but you could imagine it throwing some sort of error like it would with a Python list that just says there's nothing there. So I can do the same thing, but I can use the append inner function, which is putting stuff on the inside. So now, if I want to draw this one, bear with me, this is not very exciting to watch me draw that. Okay, so now when append inner, we were adding things to the end of the list. So we started with this, and we added this inside, and we added this inside. And so now if I get the first 3 items, they're in that order. Okay, so this is the behavior, but the behavior is not that amazing. I mean, you could have just used a Python list, and it has functions already to add things to the beginning and the end. I mean, you've used append, which adds things to the end, but there's also an insert function that you can use to add things to the beginning. So this is not giving you anything you didn't have before, because you could have just used Python list. But what we're doing today is trying to understand how these things actually work under the hood. So let's look at the code. Okay, so we have a type called treasure box. This is also called a linked list in computer science terms, but I like this treasure box analogy, or magic suitcase, or whatever. So here's how it works. You create one of these with some treasure, which is the value you're trying to store. It could be a string, could be an integer, could be another data type. It doesn't matter, right? Just like with the Python list, we can stick any type of object in here. And then, so as I said at the beginning, each treasure box contains 2 things. It contains the value, or the thing you want to store, and another one inside of it. And so I'm kind of initializing that, but setting it to none, because when I just create the original object, I don't yet have anything inside of it. So I'm putting that placeholder of I might have another box inside of it, and then setting it to none. And so let's look at append inner. So here's what append inner does. It says I want to add something to the inside of this. So if and this is a recursive function. So what we're looking at first is actually the base case. If the inner treasure box is none, meaning if there is nothing inside yet, no other treasure box inside yet, then we're just going to make a new treasure box and store that as the inner treasure box of this one. So look at this line. It's saying, I'm here. I want to add something. It's none. So I'm actually creating a new object of type treasure box, which you could think of as being over here, which had, I don't know, some stuff in it. But then when I say self.inner treasure box equals that, it's like I'm putting this inside here. I'm storing it inside my original object. So now my original object is storing another object of the same type inside of itself. But what if there was already something in there? What if you already have 5 things in your list? Well, you need to go all the way in to add it to the very innermost. If you want to add something here and you're starting here, you have to go inside of here and inside of here until you get to a case where you hit a none, where there's nothing inside. And so we do that recursively. We say, okay, well, if there was something in there, then let me just call this function on the inner treasure box. I'm just going to call append inner on the one that's inside. And then that one's going to check, is that one empty? No, it's going to go inside to the next one. Is this one empty? Yes. And so then it's going to put it in here. So the recursive nature of the data type, we have this treasure box within treasure box within treasure box, goes hand in hand with the recursive function calling of the associated functions, because it's just very natural to kind of navigate through itself recursively. Any questions or comments about this? Yeah, go ahead.
Return self, I'm not understanding.
Oh, return self, yeah. So this is not an important part of this. It's just sort of a convenience and a convention that people tend to do. That if your method in your class just changes the object, you just tend to return self by convention because it makes certain ways of using the code more clean and convenient. But yeah, it's not essential. So again, why are we doing this? As I talked about on the first day, this course is kind of split between traditional algorithms and data structures and more like applied stuff. And this part of the class is one of these traditional pieces, which is, okay, let's get under the hood and understand how these things work. You might not ever write code like this, but you are going to use things that are actually implemented like this and understand better how they work. Yeah, Leslie.
So what happens if you call this append inner on something that doesn't have an empty space at the end?
The question is, what if you call append inner on something that doesn't have an empty space at the end? So eventually there will need to be unless you have an infinite amount of stuff in your list, which we're assuming we're not, then this is always going to, you're always going to get there because you're always going to have a treasure box within a treasure box within a treasure box, and at some point you just get to the end of all the stuff that you've added, and the last one in there is going to be empty. Did that answer the question? Sort of? Yeah. Sam?
Can you explain sort of like step by step what happens when we initialize like treasure box with the code's initial box? Like walk us through the code.
Can I explain what happens step by step right here? So right here, all that's happening is I'm calling the constructor of this class. So the class is called treasure box. I'm making a new one. I'm passing in initial value. And again, these don't have to be strings. These could be integers or whatever. So all that's happening here is calling the constructor. I'm going to scroll up. So just these 2 lines of code are getting executed. It's just storing that value and creating a blank inner treasure box. And that's it for that line of code.
And then for the append outer, like for the first example.
Yeah, so I haven't got to append outer yet because so this is rather confusing, I would say, and I don't think I'm going to run out of time if I spend enough time on this that everyone understands it, but I encourage you to look at this later and we can talk about it. But let me just say very quickly how this works. So if I'm putting something on the outside, so let's say I'm adding stuff over here. and I want to put it on the outside. So I already have this treasure box, and then I want to put something on the outside. Well, I'm again calling the constructor, so I'm making a new treasure box. And then what this line is doing, which is the confusing line, is I'm saying, for this new one that I made, its inner treasure box is self, which is the current object. So I'm basically moving this thing in here. But we this use of self requires a bit more thought and discussion that we have time for right now. But it essentially refers to the current object that is actually calling the function. So since this was the treasure box that called append outer, this is the treasure box that is going to be referred to as self. So when I set the inner in here to be self, it's actually putting this original one inside, and that's how append outer works. Okay, let me see how behind schedule I am. Sorry. Okay, 15 minutes for that. Oh, not terribly. Okay, but we do need to move on. So yeah, I'd say this is not just a nested data structure like a dictionary full of dictionaries, but it's really like the definition of the type itself is that I have more stuff of that type itself inside. And so somehow recursion is flowing through the definition of the type. So I think we talked about this. We didn't look at the get function, but you can look at the get function later. It's also recursive. It's just going inner and inner that many number of times and then grabbing the value there. Okay, so that was that. Let's move on to trees. So trees are kind of the main thing we're trying to get at today and for your lab. And trees are super useful and relevant, and they're going to show up in your machine learning course and all kinds of other places. So a tree is also a recursive data structure like those treasure boxes, aka linked lists above. Except that while the treasure box just had some stuff and one treasure box inside of it, a tree has some stuff and two trees inside of it. So that's basically the only difference. But because of that, we tend to not draw them like this. We tend to draw them more like that. So here's a picture of a tree. Here's basically the outermost piece, if we're using the language we were just using of the treasure box, is the one at the very beginning. And it has some value. So in this case, general. This is some military hierarchy. And then inside of it, it basically has two more trees. So it has and then we use this terminology. It has this tree on the left, and it has this tree on the right. And then this tree on the right, again, can have a value. Okay, so this tree has more than two things, which still, officially, it is still a tree. That's okay. But we're focusing more on binary trees, where you can only have two branches coming out. Anyways, this is still an official tree. So then it has these three trees coming out of it. And so on and so forth. So you get these much more complicated structures than just with our linked list. The treasure box, where we just had some more stuff in it, some more stuff in it, some more stuff in it, and then at some point there was no more stuff in it when we stopped. Once we allow multiple of these subtrees inside, we can get these quite complex looking data structures. Okay, so yes, the exercise in 5 on your lab is you're implementing a particular type of tree called a binary search tree, whose functionality is quite similar to the Python set. So the point of that exercise in the lab is, again, someone had to make a Python set. You may not ever make one, but now you will at least do it once and understand how those things are working under the hood. Or one way that you could make it work with still a reasonable running time. Okay, so there's a bunch of terminology that we need to go through with trees. So a tree is either empty, or it is a node with 0 or more children that are themselves trees. So all the stuff below one of these nodes are called the children, or they're also called subtrees. If x is a child of y, then y is a parent of x. So Sergeant A is a child of Captain A, and Captain A is a parent of Sergeant A. The root is just a special name for the topmost or outermost or whatever you want to call it thing. So back here, the root would be like our outermost treasure box. And with the tree, it's the one that we draw at the very top, so that's called the root. A leaf is a node that does not have any children, like these ones at the very bottom. Over here, the leaf would be the innermost treasure box, but that's not very interesting because there's just going to be one. With the tree, you can have a whole bunch of leaf nodes. And an internal node is a node that is not a leaf. And the height of the tree, also called the depth of the tree, is basically the largest number of times you have to recurse until you get to the bottom. So from here, from the top to the bottom, it's 1, 2, 3, 4 steps. And so you would say the height of the tree is 4. So that's just a bunch of terminology that we might use when talking about trees. And so like with the treasure box, what we're going to do is actually code up a simple tree and then talk about it and talk about the code. And this code is relevant for what you need to do in the lab as well. So let's actually just start with this part, the constructor. So like with the treasure box, in this case I'm calling it label. Before I called it treasure. It doesn't matter, value, thing you want to store, key. It's the thing you're actually trying to store. So I just called it label here because we had those, general, captain, etc. And then we have 2 empty spaces because this particular code that I'm showing you is an implementation for a binary tree, which just means you're only allowed 2 children for every node. So the constructor actually so far looks very similar to the treasure box one, except we just have those 2 empty spaces instead of 1. And now, I don't actually have code here for how do you put stuff in the tree, because you're going to have to figure that out on your lab. But here's a contains function. So I want to check if a certain label is in the tree. So I build the tree, and I want to know, is the President of the United States in that tree that we looked at before? So here's what I'm going to do. If the thing I'm looking for, the target, sorry, it would have been better to keep the variable names more consistent across the 2 things. My bad for that. If the thing I'm looking for, the target, is the thing stored in the tree I am looking at right now, then I'm going to return true, because that means I have found what I'm looking for. So yes, the tree contains the target because I just found it. I'm looking at it right now, so I return true. But if not, well, let's go back up to this tree up here. And let's say I'm looking for, I don't know, Sergeant B, and I'm starting up here, and this general is not equal to Sergeant B. So what do? Well, I recursively look. Is it in my left subtree, and is it in my right subtree? And I, again, just trust the recursion to do its job properly for those 2 things. And if it's not anywhere in the left subtree and that has been computed properly, and it's not anywhere in the right subtree and that has been computed properly, then it's not anywhere because, well, it's not here, it's not over there, it's not over there. So the code looks like this. Yeah. So I'm using these inline if-else statements, I guess. Well, we'll just stick with it. So if self.left is none, meaning if I don't have a left subtree, because I never put anything there, then there's definitely, the thing I'm looking for is not in my left subtree because I don't even have a left subtree. So I'm not even going to bother. So in that case, I'm just setting that to false. The left subtree does not contain the thing I'm looking for because the left subtree does not even exist. But otherwise, if it's not none, then I want to call contains on that left subtree. I want to say, well, I'm looking for President of the United States. It's not right here in front of me because that says general. Do I have a left subtree? Yes, it exists, so go look in there. And so I'm recursively calling contains on that subtree. And critically, that left subtree, the data type of self.left is itself binary tree. Just like with the treasure box, the data type of the thing was another treasure box inside of it. The data type of left and right are also binary tree. So it's totally valid for me to call the contains function on self.left because self.left is a binary tree and binary tree has a contains function. Yes, weirdly, we're in the middle of implementing it, and that's kind of the weird thing about recursion. But assuming it all works out in the end, I should be able to call contains on that, and whatever it finds, that'll be it. And then I do the same thing on the right side, and then I just return left or right. So if it's in the left or if it's in the right, then I found it somewhere. And if those two things are both false, then I didn't find it anywhere. That's how the code works. This is a lot to digest. Let me just show you a bit more code and then I'll take questions. So here's an example of using this. I make a binary tree with the root as general. In this case, I'm just manually setting the left and right to subtrees because I didn't actually put in a proper add function. So on the left, I have kernel A, on the right, kernel B, and then going to the right, and then to the left, I have captain A and captain B, and so on. I need to run this. And then I want to say, does the root contain clown? And then does the root contain captain B? And again, does the root contain captain B means is captain B anywhere below the root? Because that's what the contains function does. It doesn't just mean is it right there. So I'm hoping to get true here. And I do. And just to reiterate, the root is a binary tree. We know that because we just made it up here. But the left and right are also binary trees. And so that's kind of what keeps this all together. The binary tree is made up of the value and two more binary tree types. Questions about this? Ryan.
So when we first start searching, we're looking at a particular node, and if it's not the result, then we start searching on the left and searching on the right.
Yep.
But we search on both sides before we return some value.
Yep.
Let's say both sides are pretty full of nodes.
Yep.
And what we're looking for is on the right side. Even if I find what I'm looking for on the right side pretty fast, it's still already started a search on the left, and it's going to have to go through that exhaustively or pretty exhaustively. Right?
So Ryan's question is, this looks a bit inefficient because maybe there's a ton of stuff on the left and the right, and I call left contains and it's already true, then why would I bother searching on the right? Because I already found the thing. So yeah, that's totally valid. There are ways of speeding this up. Even the OR inside of Python kind of takes care of those optimizations, not in the way I wrote it. But if I threw this all into one giant line of code, then that would actually be handled automatically. But yeah, you're totally right. I could also just do, if left contains is true, return true, and that would basically solve the problem. So yeah, this implementation was not designed for maximal efficiency.
Okay.
What's your name again?
Simmer.
Simmer.
So for the class treasure box, we initialized the self.inner treasure box. But in this case, don't we need to initialize self.left?
Yeah, the question was, don't we need to initialize self.left? So yeah, ideally you would have a function here that would add something to the tree, for example. I just didn't want to write that function for you because I'd be pretty much giving away the whole lab. So yes, the treasure box had an append inner and append outer, and those actually created new things and set them all the right places. And you would want something like this. I just didn't implement it, and then I did this kind of gross thing instead of just directly setting them, which is not how you would actually want to do it. But I didn't want to give you all the code. Leslie.
So if left contains and right contains don't actually find what they're looking for, then contains just doesn't return anything.
If left contains and right contains do not find what they're looking for, then this is going to be the Boolean value false. This is going to be the Boolean value false. The OR of two falses is going to be false, and so it's just going to return false.
Oh, got it. Okay.
Furkan.
So in the last lecture, we talked about the hash tables, and now we are talking about the binary search trees. So which, let's say, model is used to create sets in general?
Yeah, so the question was, we talked about hash tables, what is typically used to create sets in general in languages. So I don't know about every language. In Python, the built-in default set does use a hash table rather than a tree, but the tree is still pretty good. So at the end of the day, I don't know if this is a question that I'm about to ask you that I'm going to give away. I don't think so. Anyways, at the end, the time it takes to run this contains is log n if you do it all properly, and you're going to actually time it in the lab and see that for yourself. So the hash table is constant, which is slightly better than log n, but honestly, they're both super good. And the thing you really don't want to do is have it be linear time. That if you want to check if something is in there, you just go through every single element and say, is it this, is it this, is it this? That's super slow. So both of these are fine. Yeah, Python uses a hash table by default. And there's some minor pros and cons, but I don't know. I guess maybe a hash table is more popular, but I don't know. Yeah, Rob. Matt, yeah.
Should we be using inline if-else statements or nested if-else statements?
Should we use inline if-else statements or nested if-else? It doesn't matter. It's just a matter of style. If it's readable, then it's fine either way. If it becomes like a 200 character long line, then don't do that. But yeah, it's personal preference at some point. Okay, so the key idea here is that like TreasureBox, a binary tree object stores more binary tree objects, but here we're storing 2 instead of 1. So a binary search tree is a particular type of binary tree that has this kind of sorted or ordered property to it that for all nodes, all the keys in the left subtree are smaller than its key, and all the keys in the right subtree are larger than its key. So you could have 5 over here, and then you could have 3 over there, and 10 over there, and 1 over here, and so on and so forth. So in the tree we had above, there was no such constraint. Like I could put -1 over here, and it would be fine in the code I showed you. But in the code you're going to write in lab, it has to maintain this sorted property, and that's what it's going to allow it to search so fast. Because right now, our contains function, so I misspoke earlier. Right now, our contains function does end up actually looking through the whole tree. It just looks through recursively. So it is O of n time in the code I showed you on there, because you don't know where to look. It could be here, it could be there. But when you keep this ordered in your lab, then basically if you're looking for 6 and here is 5, then you only need to look to the right, and that's that ripping that phone book in half and throwing half of it away. You could just ignore the whole left subtree if you're looking for 6 and there's a 5 up here. So that every time you can just throw away half of the tree and only look down one of the 2 branches, and that's what gives you that log n lookup time. Annie?
So for the term binary tree, does it have to have a time of O log n?
No. So a tree is just the most general term. You could have like 5 children in a node or whatever. Binary tree only restricts it to just having 2 children in a node. And then binary search tree further restricts it to having this ordering property, which is what you're doing in lab. That was my mistake.
Thank you.
Jarvis?
How would you sort labels if you were not using numbers?
How would you sort labels if you're not using numbers? Right. So in the lab, I basically say, don't worry about it. And you can just use the greater than and less than symbols. And for a bunch of types, Python just decided a way to compare things. So for example, in the lab, you have strings, and it just sorts alphabetically. So this should be true. So basically, anything that you can check if this one is less than or greater than the other one, you can use your binary search tree for. Which, and I think I had this somewhere in the notes, right here. So to contrast that with the hash table that we talked about before, the requirement to be able to put something in the hash table as a key was that it has to be hashable. The requirement for the lab is that all the keys you put in have to be able to be compared to one another. So typically they would all be integers or floats or strings or whatever. Okay, so complexity. So binary search trees could actually become very slow in a pathological case, which is that if you first put in 1 and then you wanted to add 2, well, 2 is bigger than 1, so 2 is going to go to the right. And then if you next put in 3, well, 3 is bigger than 2, so 3 is going to go to the right, and so on and so forth. So if you pathologically added things to your tree in sorted order, then your tree is actually just going to become a chain. And then lookup will actually take linear time because there's only one way to go. So in the part of the lab where I ask you to do experiments timing things, I intentionally pick random numbers so that you're putting things in a random order and you will kind of avoid this phenomenon. But industrial strength tree implementations will do something called balancing the tree. So if this starts to happen, it'll automatically reorder the nodes, and so everything will kind of work out. But the details of how to do that are outside the scope of the course, and the details of how to delete stuff out of the tree is also not something we're going to go into, but you could certainly read about. So what we're going to talk about for the rest of today is nearest neighbors. So a very common problem that you'll see in supervised learning course and unsupervised learning course and all kinds of places is finding points that are close to each other. So what does that mean? Well, don't worry about this plotting code, but here's some points in a two-dimensional diagram, and I have this red point, and I just want to find out which of the blue points are very close to the red point. That's called nearest neighbors. And this problem comes up in a lot of places, as you'll see. Unfortunately, the motivation is coming in later courses. It's usually better if it's the other way around. But anyways, well, how do we find the blue points that are closest to this red point? So first we need a notion of distance. And for now, we'll just talk about regular old Euclidean distance, like the distance you're used to between 2 points on a map or whatever. Yeah, square root of the x difference squared plus the y difference squared, that kind of thing. So here's a potential algorithm for finding the closest points. Just loop through all the blue points, compute the distance between the blue point and the red point, and then find the smallest ones. Okay, that does work. That is a correct algorithm, but it's slow because it's O of n time, where n is the number of blue points. And as you'll see in those later courses, sometimes n could be huge. Like sometimes it might be all the products for sale on Amazon or something like that, because just to kind of give you a preview, on Amazon you have those related items. Here's some items similar to this. And you could think of each item as basically a point in some space, and you want to find similar items so you can show them to the person at the store. And if you needed to go through every single thing for sale to find the closest item to a particular thing that a person is looking at, well, O of n is not going to cut it there, because there might be, I don't even know how many things are for sale there, but millions easily. So O of n could be way too, I don't know, maybe a lot more than millions. Okay, so first of all, I have some code that just does the O of n thing I just talked about. We're not going to go through the code right now because it relies on some stuff that you haven't yet covered in the data wrangling course. But let's just say we have some code that does this. So here is x. X is my data set. So we had that picture earlier of all the blue points. this is basically what all those blue points look like when they're stored in a Python variable. Each blue point has an x coordinate and a y coordinate, and so the first row is the first blue point. The formatting is pretty gross, but the e-1 is times 10 to the -1, so that first point is 0.4, 0.7, and so on and so forth. So each point is an x and y, and each one is stored in a row of x. And so here was my red point, which happened to be 0.5, right in the middle of that canvas that I showed you. And I can just call this nearest neighbor function that I wrote. And what it does is it actually sorts all the blue points by which one is closest. So apparently, blue point number 8 is the closest, and then blue point number 4 is the next closest, and blue point number 5 is the next closest, and so on. And so this is, well, just to find the closest is O of n. This is actually n log n because there's some sorting, but we don't really care about that distinction. So, well, let's just take x of 8. So apparently the closest point to the red one, which is 0.5, is, according to this, number 8. What is number 8? Well, it's at 0.4, 0.55. And if I scroll back up, I can see that 0.4, 0.55, it's probably this blue point right here where my mouse is. So that all checks out. It seemed to work. And it told me that point number 8 was the closest. So any questions about this kind of setup before we move on? Oh, Jerome.
8 is the name of the tuple for the coordinates?
Yeah, 8 is the index, because I've actually just stored all the blue points in a two-dimensional array where each row was one of the points. So it's basically saying row 8 of that was those coordinates.
Okay.
Other questions? Okay. So, and yeah, we could find that. So the next closest was 4, according to this output here, and this 4 actually looks pretty close as well, and that was that other blue point that was very nearby as well. So what is the time complexity of nearest neighbor? Well, we said it's O of n. Let's just say, not really let's just say, what is the time complexity of finding the closest neighbor? I'm getting caught up in this sorting, but I don't want to get into that right now. So just finding the single closest neighbor. Well, I have to search through all possible points. So that's O of n if I want to find the single closest neighbor. But another thing is, what if we have k dimensions? So this was all in 2 dimensions. We just had an x coordinate and a y coordinate. But in reality, you might have points in more numbers of dimensions. So with the Amazon thing, you might have a whole bunch of properties describing an item. Maybe you have 100 properties or 1,000 properties describing an item. And so now it's like you're in 100 dimensions trying to find what is closer to the other. And so the question is, well, how long does it take to actually find the distance between 2 points? That's going to be O of k, because I have to find what's the distance in the x direction and what's the distance in the y direction. But if I have 100 of these dimensions, I just have to sum up all these squared distances and square root them at the end. So the overall time complexity is big O of n times k. So I basically have to, and another way you can see that, by the way, I'm just going to scroll up here, is this x array that's storing all the points. Well, how big is that x array? It has n rows, because I have n points, and it has k columns, 1 per dimension. And so the amount of stuff in x is n times k. And so I'm going to have to go through all of that stuff at some point to get the job done. And so that's my O of n times k right there. Okay, so yeah, as I said, this may be way too slow because n and or k might be large. Okay, so how do we make it faster? I'm going to introduce something called a KD tree, which is a data structure that is more or less for solving this problem. So I mean, talking about like a list or a dictionary, like there's so many things you might use a list for. There's so many things you might use a dictionary for. Even a set, maybe it's slightly more specialized, but there's so many things you might use a set for. But sometimes when you get to specific problems, then we get to specific data structures, which are pretty much there for just solving that one problem. And this is an example here. And the reason why I'm changing gears so suddenly into this nearest neighbors thing in the middle of this course is that a good way to address this problem is actually with the type of tree. And we just talked about trees, so I thought, well, maybe it would fit together. So what is the plan here? Well, actually, let me first ask, are there any questions about the kind of intro to nearest neighbors? Ryan?
Yeah, when you say the time is O(nk), that's ignoring the sorting, right?
Yeah. So the time O of nk is just to find the nearest neighbor. Then you have to look through everything. Okay, so yeah, sometimes we speed things up with faster algorithms, and we're going to do a lot of that towards the end of the course in Lab 4. We're going to look at a particular problem and a bunch of different algorithms and see that some are much faster than others. And sometimes we solve our problems with better data structures. So, well, yeah, in a way we've been doing that as well in this course. So one way to speed up the nearest neighbor problems is called a KD tree. So it's going to say, let's not store those n points in that 2D NumPy array X where each row is a point and the columns are the coordinates. Let's store those points in some other data structure, and then we can find nearest neighbors faster. And actually, that's pretty much what we've been doing earlier today with the binary search tree and what you're going to implement in lab in a set. It's like, if I want to do lookups in a set, does the set contain this? Does the set contain that? Well, instead of just storing it all in some sort of list where I have to look through every single thing, I'm going to be clever and store it in some fancy data structure like a binary search tree so that the thing I want to do is fast because I've kind of prearranged the data nicely. And even with binary search that we saw in the first week, last week, we talked about you first sorted the list and then everything was fast. And again, sorting it is sort of like a special way of storing the data to make things fast. So let's get right into it. So yeah, here's a bunch of code that we don't have time to look through, but you are welcome to look through later and ask questions. It's just an implementation of this KD tree in Python. But here, I want to talk about how it actually works. So we had a bunch of those points, and here they are again. So remember, the blue points are the only ones that we have in advance. And then we want to, the red point is like the query, which it's analogous to like, is this in my set? Is that in my set? So we want to be able to check for any possible red point. We want to be able to quickly find the nearest neighbor. So for anything you might be looking at on Amazon, we might want to be able to quickly find the similar item. So here's the points, and here's what the KD tree does. So alternating between horizontal lines and vertical lines, but here we just arbitrarily started with the vertical line. We find sort of the halfway point through the data set, which is defined to be the median of the x coordinates of all the points. So we take all our points, we take all their x coordinates, and we take the median, and that's how we get this blue line. So half of the points are on the left of it, and half of the points are on the right of it. And then this is sort of going to be like the binary search tree that we just talked about, because what's going to happen is if we want to find the nearest neighbor of, say, the red point 0.5, 0.5, well, we have stored that split line, which is around, I guess, x equals 0.25. So we're going to say this thing that we're looking for, the red point 0.5, 0.5, which side of that line does it fall on? Its x coordinate is 0.5. Is that greater than the line or less than the line? And so in that sense, it's kind of building up a tree in the same way. And we say, oh, 0.5 is greater than the line, so let's only restrict our search to the stuff on the right half. And that's kind of this throwing away half the phone book thing that we like to have, that we just immediately do one comparison, and then immediately throw away half the problem. And because it's the median, it's exactly half the problem because we picked the line that way, so that half the stuff is on the left and half the stuff is on the right. So now to find the nearest neighbors, roughly speaking, we only have to look at half the data set. And then if we had another such line that was dividing the data set in half, which, by the way, is this, then we can do it again. So like a tree, we are recursively taking the two sides. So we've kind of branched the tree at this vertical line. And then for each of the two sides, now we have like half the data set over here, half the data set over here. We did the same operation, but on the y-coordinate. We said, what's the median of the y-coordinates in this half? What's the median of the y-coordinates in that half? And we drew the line. And now again, so these lines are all drawn kind of the same on this picture, but it's misleading. This line here is sort of the root of the tree. That's like the first division. And then these two lines over here are kind of the next branchings below it. And so now if we wanted to look up 0.5, 0.5, we would say, well, look at the x-coordinate. It's bigger than 0.5, so it's on the right side of this line. Now I only have to think about the right side of this line. And now we take the y-coordinate, and we say, oh, it's less than this thing, 0.7. So now I've thrown away half the data set again. And suddenly, I only have a very small number of points to look through to find the nearest neighbors. Andy?
But what if your red dot was like right under that horizontal line on the right?
Yeah.
Ignore all of the blue dots. Pretend there's only one blue dot, maybe 1 point above it on the other side of the line.
That's a great question. So I don't know exactly where you were referring to, but let's say your red dot is right here where I put the cursor. So you're right. In that case, this is going to lead you astray because the true nearest neighbor is in a different partition, and you've ripped that part of the phone book and thrown it away. So you're not going to actually find it. So, okay, two things. First of all, the code that I have given you here, which we didn't look at, actually implements an approximate nearest neighbor. So it may give you the wrong answer, but at least it's fast. However, well, wait a minute. That might not be so bad, because think about the Amazon thing. I mean, do you really care about getting the most similar item in all of Amazon to show the person, or do you just care about getting something pretty similar to show the person? You actually might not care that much. So the first thing that we just need to talk about is sometimes you actually don't care about getting exactly the right answer. And if you can let go of getting exactly the right answer, you might open the door to way faster algorithms. And sometimes that's something we need to think through, and a compromise that's worth making, and just like an option that's worth considering. Having said all that, for KD trees specifically, there is a way to make it exact that is only just slightly slower than my implementation. So it just does some extra correction, checking, make sure that doesn't happen. And then it does give you the exact answer, but then the code is way too complicated for me to post there. So in this case, you can actually get the best of both worlds. You can make it fast. And I'm going to show you in a minute a Python package that does that. But just for the purposes of the discussion, I'm showing you the approximate version that could be wrong. That was a great question. Any other questions? Yeah, Leslie.
So why is it that, so you make the first division as the median of the x's, and then you want to look at the median of the y's. Why is it y instead of x?
Yeah, the question is, why are we switching from the x-coordinate to the y-coordinate? So need to think about that for a minute. The thing is that if you just kept splitting it by the x-coordinate, then according to what I said, you would still be splitting the data set in half every time. I'm going to guess that it has to do with this thing that I just talked about, that if you did that, you could actually get something that's horribly wrong, and the stuff to make it not wrong would no longer work or something like that. So good point, but I think you need to do something like this to get it to work perfectly in the end. Brendan?
Yeah.
Brendan.
Yeah. Maybe you're headed there. I haven't looked ahead, but if you're doing this on multiple different attributes, are you slicing according to each attribute?
Yes.
Yeah.
Yes. So here I just have 2 dimensions or attributes, and so I'm just alternating back and forth x, y, x, y. But if you had more, you would have to be like cycling through them essentially. So x, y, z, or whatever. Yeah, so I do have the plot for the next one, but it starts to not really look like anything. I mean, maybe it's helpful for you, but to me, this is too much to really digest. But I guess all we can, at least it's a little less painful if we compare this one to the previous one. So first we divided vertically, then for each half we divided horizontally, and then for each quarter we divided vertically again. But I don't know, to me it's just, because the picture doesn't convey that there's a hierarchy here, it's just a bit hard to digest. But yeah, here's the last one that I have. Okay, so look, I even called the function approximate nearest neighbor. So I was owning that it wasn't quite right. Just a second, Tom, I want to just get through this. So I can call this function approximate nearest neighbor on a query point 1, 1. And I can also use my very slow linear time nearest neighbor thing that I showed you before that just looked through every single point. And they agree, so that's good. But I think I picked the next case where they would actually disagree. Yeah, just to show. So this is actually wrong, this one over here. That it's not showing the closest point to 0.5 because of the point that Annie brought up. But it's still a somewhat nearby point, and again, there is actually an algorithm that is also fast that does it right. It's just complicated. Oh.
Good question. If a point's on like a boundary line for the median, what group is it?
Yeah, the question is if the point is on the boundary line for the median, what group does it go in? That is kind of arbitrary. I'm going to scroll up now to the code. Oh gosh. Here, so that's basically arbitrarily defined right here by this less than. So if it was less than or equal to, then it would be the other convention. So I guess the fact that I use less than means it goes with the bigger side, but if I use less than or equal, anyway, it ends up not mattering. And this is a pattern that you'll see a lot when you're writing code like this, is you just make an arbitrary choice between less than or equal to, and it doesn't really matter. Sam.
In regards to the depth, how do you know enough is enough without like...
Yeah, oh, great, right. So Sam's question is, how do you know enough depth is enough? So yes, I forgot to mention that. So the actual way the algorithm goes, we can look into the code just a little bit, at least to look at the base case. So the base case of this recursive, by the way, this is the recursive tree building code. The base case just says if there's only one data point in my region, then I'm done. So the implementation I have here just keeps splitting and splitting and splitting until each data point is like in its own subregion. And so you're going to have roughly like log n depth. Victor.
Do I need to cut all the dimensions, or can I do it like randomly and maybe take ones and not others?
Yeah, so I think this most standard implementation is you just cycle through the dimensions, so x, y, or x, y, z, x, y, z. Maybe randomly would work, I don't remember all the details, but I'm pretty sure you can't just take the same dimension over and over again.
I think if you just
Alexander?
X, you would just end up with whatever point was closest only on that axis.
Right.
Instead of actually closer.
Yeah, so Alexander was saying if you just take the x-axis every time, then you end up with the point that's closest only on that dimension. Right, so I guess that goes back to what the code I have is wrong, but like then it could be very horribly wrong because you might have something that is very close on x but super far away on y and you've never even looked at that. So I think then it would be kind of unfixable.
Yeah, I just wanted to say the same thing.
Okay.
Except I think if in terms of features, if we take it, would be ending up closest to a single feature.
Yeah, same thing. Yeah, thanks. What's your name?
Jack.
Jack.
So what if we did like x, y, x, y, then you have y, x, y, x? You like find two separate points and compare those two.
So you're saying like build two trees, one that started on X and one that started on Y? I don't think you need to do that, because as I said, I think there's some other way of fixing the problem that is, the code is very painful, but it's not actually that slow. And that's what is typically done as far as I know. I suspect what you suggested probably could still be wrong, although I'm not sure. Jerome?
So this works if you're working with numbers, you can take the median and do the less than. For the Amazon case, it's like products. So do they like make them numbers then do this?
Yeah, great question. So the question is, this works with if all the points are like numerical numbers, because you can take the median, say less than, greater than, all those things. But what about if you have products, like where do you get numbers? So that is a great point. It is going to come up. Varada is here. She'll explain this to you in Supervise 1. We'll probably talk about this. In feature and model selection, you'll probably talk about this. So yes, this is a real problem that is a pain in machine learning in general, that you would just love everything to be numerical, and often it isn't. But I'm going to skip that one for today in the interest of time. But yeah, yes, it is an issue. Okay, so scrolling. Holy cow. Okay, so yes, this doesn't work perfectly, but there is a correct algorithm, and there's a package called scikit-learn, which you're going to be using in those future courses that I mentioned, and they have implemented KD tree much better than I have. And what's nice about all these packages is they're open source, so if you really want to, you can click on the link, and you can actually look at their code if you're interested. So two things. First of all, KD trees are pretty good, but they're still not the be-all, end-all of nearest neighbors, because they can actually be pretty bad when k is very large, when the number of dimensions is very hard, and there's some other methods as well. But I want to start timing some code. So here's what I do. I guess you've now seen this type of code in my lecture 2, and then at the end of lab 2 that you're working on this week, you do this binary search tree, and you do more code like this as well when you're timing it. All I'm doing here is I'm timing how long the scikit-learn thing takes, and then I'm comparing it to my code that I showed you earlier, which does basically the brute force look through every single point. So I'm running it, and then I'm just fixing, we're calling this k. I'm just fixing k as 10, so I have 10 dimensions, so each point is a point in 10-dimensional space, or meaning each point is a list of 10 numbers, basically, instead of 2, like we had. And then I'm changing n from 100,000, 10,000, 100,000, and we're just going to see how fast the two methods are. But in order to not cheat, the other thing I'm timing is how long does it take to actually make the KD tree? And that's something some of you have been bringing up. Like, wait a minute, it does the thing really fast, but how long did it take to actually make the thing? So there's an optional question on Lab 2 where you explore that as well, and here we're showing it. So we're timing 3 things. How long does it take to make the KD tree? How long does it take to find a nearest neighbor, do a single lookup with the KD tree after it's made? And how long does it take to just find a nearest neighbor by searching through all possible points and just saying, is this the closest, is this the closest, etc. Okay, so this is done, and here's the results. And so here's what we see. Actually, initializing the KD tree is very slow. It is much slower than everything else. So for the last column here, initializing the KD tree takes 0.1 seconds, which is more than just doing the brute force search. So this brings us back to something we've talked about before, which is if you're just going to do it once, if you're only going to do a single nearest neighbor search, even if you have 100,000 items, it's not worth it making this KD tree. You just look through all 100,000 things, bite the bullet, it takes you 18, 19 milliseconds, fine. I'd still rather do that than spend 100 milliseconds making this KD tree. So the benefits here come from if you have the same data set once and you just want to search over and over and over again, which could happen with Amazon, right? They have all their items and now there's people doing stuff all the time, and you might want something like this. And this has been a theme that has come up a few times in the course. So should I bother making my fancy set? Well, if I'm only going to look up one thing, maybe not. But if I want to be looking things up all the time, sure. Should I bother sorting my list to do binary search? Well, if I'm only going to search one time, then maybe I'm not going to bother sorting my list. But if I'm going to do a bunch of searches, then yes, it's worth that overhead cost. So we're a bit low on time, so I'm going to skip ahead a bit. But basically, there's this idea of amortization, which is that if I'm doing 1,000 lookups, then I can think of that initial cost as being kind of shared over those 1,000 lookups. So if it took a second to make the KD tree, and then I'm going to do 1,000 lookups, I can kind of think of that as, well, it's just like a millisecond per lookup overall that I spent on this overhead of making the tree. And that's called amortization or amortized time. So here, for a particular run that I did, making the KD tree took 4 milliseconds. And look at that, the query is much faster. That's the whole point of all this we talked about, is the query was 10 times faster. We went from 1 millisecond to 0.1 milliseconds. That is good, right? Because we wanted to query faster. That's why we did this. We can query 10 times faster. That's great. But it's not worth it if we're only doing one query. But once I do 5-ish queries, then it already pays back that initial cost of building up the tree. And if I'm doing 1,000 queries, then it's way, way better to make the tree. Okay, I just have 1 minute left, so I'll just quickly say there's other ways of doing nearest neighbors other than KD trees, and they're outside the scope of the course, but you can read about them if you like. I put some links to you. There's, just like with sets, you can have sort of the hash one and the tree one. With this nearest neighbor problems, there's also hash-related solutions. And again, I just think it's a nice idea to take away that this thing I have in italics, that if you're okay with the result being slightly wrong, then often you can do things a lot faster. And more often than you expect, you might actually be okay with doing stuff slightly wrong. So that brings up this whole thing of approximate algorithms, as they're called, that are actually quite useful. We are out of time for today, so I'm going to leave these true-false questions, but feel free to look at them. Feel free to start a discussion on Slack about them, and we can answer. But we'll have to stop here for today. So that's it. I'll see some of you in lab, and I'll see the rest of you next week.